let's take a look at Taylor Polynomials Day 1. Okay, let's move this. So we talked last unit about being able to approximate certain things. Maybe we have a function that is impossible to integrate. And we looked at some approximation techniques last unit. The Taylor polynomials and the Taylor series and Maclaurin series are approximation techniques. What they're going to allow us to do is approximate functions that are more difficult to work with. We know that polynomials are pretty straightforward and easy to work with, and so mathematicians have come up with a technique to approximate different types of functions with a polynomial. That's what we're looking at here, Taylor polynomials. Now, let's look at what that is basically. Let's look at this diagram right here. The blue line is sine x, and these other things are representations of a Taylor polynomial. If we'll look at this gray one is first degree. Let's see, this one right here, the orange one, is the third degree Taylor polynomial. The red one is a fifth degree, and this purple one is a seventh degree. So hopefully as you look at that, you will notice that the higher degreed Taylor polynomial we use, the more accurately it approximates the original function. A 1 degree Taylor polynomial isn't a whole lot of good when we get farther away from 0. But look at the 7th degree. See, it's really close all the way up to pi. I mean, you can pretty much not even hardly tell it apart from the original until we get to around pi, and then it breaks off. So the larger degree of polynomial we use, the more accurate our approximation is going to be. So this is a graphical representation of what a Taylor polynomial will do. That's what it's used for, is to approximate a particular function. So let's look at how they're generated. A Taylor polynomial can be centered pretty much anywhere. It's centered at C, and what I mean by centered is that's where it's generated from. Centered in this particular one is actually, these polynomials are actually centered at 0, which is a Maclaurin polynomial. That's just a special type of Taylor polynomial that's centered at 0. And this one, you can tell, is centered at 0. They all converge at 0. That's exactly where they all match. Where they're centered is where they're all the same, is where it's centered. Then as we go out from the center, we become less and less accurate. So the more closer we are to this place where the polynomial is centered, the more accurate our estimate is going to be. So it's a pretty important concept for you to get. Taylor polynomial, we can center it anywhere. We're centering it at C. And let's look at see how they're generated. What we do is we take the function value here at C. This next term, we take the first derivative, the function value at the first derivative, multiplied by x minus c. The next term, we take the second derivative value at that centered location over 2 factorial times x minus c squared, and then we continue. We would do the third derivative at that value over 3 factorial times x minus c cubed. When these get fairly complicated, when I have a lot of terms to work with, this pattern really helps me. That notice it's the second derivative over 2 factorial, and this term right here is to the second power. So they're all going to match. And with the 3, it's going to be the third derivative over 3 factorial, and the power is going to be to the third. So that usually is quite helpful for students to remember how to generate the polynomials. This is one of the topics actually that students usually have a very easy time generating the polynomials. Alright, so let's do an example. Let's talk about this n value, n equals 5. This means we're going to do a 5th degree Maclaurin polynomial. And you need to know when it says Maclaurin that means it's centered at 0. It's like a vocabulary word. They're not going to tell you necessarily that it's centered at 0. You have to know that. This stands for the degree. And if we look at how this polynomial is generated, this first number that we come up with is just a constant. It's just a constant. And then I have, the first degree, second degree, third degree. So if I don't have any 0 values for any derivative values, that would mean that I would have 6 terms for an n equals 5. I would have a constant and then up to, my 5th degree. All right. So what I usually do when I'm working on one of these, I have like a piece of scratch paper out to the side because I'm going to have to generate 5 derivatives for sine. And I'm going to have to generate the function value, each of the derivative values at wherever I'm centering. Here I'm centering at 0, so I'm going to want to have, f prime of 0, f double prime of 0, and so forth. So I'm going, for space sake, I'm going to write it here, but then I'm going to have to kind of erase. So let's generate our first 5 derivatives. So our function is sine. So we have f prime of x. So the derivative of sine is cosine. And I go ahead and do my function, or my centered value here. We are centered at 0, so I go ahead and do f prime of 0. Might as well when I have the function up here. So cosine of 0 is 1. So then we go to the second derivative. And the derivative of cosine is negative sine. And so I go ahead and do my second derivative value at 0. So negative sine of 0 is just 0. Then we do our third derivative. The derivative of sine is cosine, so the derivative of negative sine is a negative cosine. So my third derivative value at 0, let's see, cosine of 0 is 1 times negative 1. That's going to give me a negative 1. Once we get past the third derivative, usually they just put numbers or Roman numerals, something like that. I'm just going to put numbers. So f4 of x, so the derivative of cosine is negative sine, so the derivative of negative cosine would be positive sine. And then my value, my fourth derivative value at 0, it's going to be 0. And our last derivative that we're going to generate is the fifth one, and the derivative of sine is cosine. And then my fifth derivative value, let's see, cosine of 0 is 1. So what I'm going to do is I'm going to write the whole polynomial out, even with the 0 terms, so you can see how I'm generating it. Once you get used to these, you'll just know that you don't even write the 0 term part out because the 0 wipes the whole term out. But I'm going to go ahead and just follow this formula right here. And just for space sake, I'm going to go ahead and put it up here. So this is going to be P5 of x. So the first thing that I would do is I would take the function and I would put that centered value in it, which is 0. So sine of 0 is 0 plus. Then I would take my first derivative value, which is a 1, and multiply it times x. We're using the Maclaurin right here. We're using this. Might be easier if I wrote it down here, maybe less confusing. 0 plus 1x. Alright, then the next one, we're going to do the second derivative. The second derivative value is 0. So plus 0 over 2 factorial times x squared. Okay, I'm just using this pattern right here. Then my third derivative is a negative 1. Negative 1 over 3 factorial times x cubed. My fourth derivative is 0. 0 over 4 factorial times x to the fourth. And my fifth derivative is 1 over 5 factorial times x to the fifth. So hopefully you can see the derivatives that yielded a 0. This whole term is going to be gone, right? I mean, I didn't even really need to write it. The only reason I'm writing it is so that you can see how it was generated. So let's clean it up. P5 of x is going to be, let's see, we have an x, and then that term is wiped out. Then we have this one, let's see, 3 factorial, 3 times 2 times 1, that's 6. So we have minus 1/6 x to the third. My fourth degree term is wiped out with that 0. And then I have 1 over 5 factorial, I think is 120, plus 1 over 120 x to the fifth. And that is my, actually, it's a Maclaurin polynomial because it's centered at 0. That's my fifth degree Maclaurin polynomial for sine. This actually is represented over here on the graph by this red one right here. This one is the fifth degree polynomial for sine. This is a graph of this, just so you can see how it actually looks. It's a pretty good representation. It matches sine until it looks like about right in here. Then it starts going, the error starts becoming greater. So if they ask us to find P5 of 1.2, what they're asking us to do is substitute 1.2 in our polynomial and get our decimal approximation. Now for these, I usually go out about 6 decimal places because sometimes the differences in them are going to be just nuances. So I usually just go out 6 decimal places and truncate. That's just what you'll see me do. You don't have to truncate. You could round if you wanted to, but that's just what I do. So I went ahead and I had my calculator and I substituted the 1.2 in this polynomial, and I got 0.932736. 0.932736. And that is the the Maclaurin polynomial value. Now when they ask us to find f of 1.2, what they're asking us to do is actually put that in our original function. Find f of 1.2 is sine of 1.2. So we would make sure our calculators are in radian mode, and we would just type that in our calculator, and we would get sine of 1.2, and that would give us 0.932039. Now we're going to talk about error. We're working with approximations, so we know we're going to have to deal with the error. The error in our approximation is quite similar to the error that we were working with last unit with the alternating series error, where it's the absolute value of the real value minus the approximation. So the real value was 0.932039. minus the approximation, which was 0.932736. And so I just put those in my calculator, and I get my error 0.000697. That was a pretty good approximation, wasn't it? And if we look at the graph, it would make sense. If we are at 1.2, which means we are somewhere in here. Oh, this is by pi. Pi over 2, so it would be over here. That's pretty close. I mean, that's a pretty close approximation. We are only, 0.000697 off from the actual value. All right, we're going to use the same polynomial, and we're going to look at our polynomial approximation of 2.1. Now, do you think that's going to be a better approximation or a worse approximation than at 1.2? It's going to be worse, right? Because it's farther away from where the polynomial is centered. The closer you get to, this polynomial is centered at 0. The closer you get to 0, the better your estimate is going to be. If you are trying to use a polynomial centered at 0 and you're trying to find an estimate out at 5, are you going to get a pretty good estimate? I mean, no, it'll probably be awful. So you just need to keep that in mind as you're working with it, that the farther away you are from the center, the less accurate your estimate is going to be. So we would put the 2.1 into our polynomial right here, and we get 0.8968, 0.896841. And then we actually find the for real value, f of 2.1, which is sine of 2.1, and we get 0.863209. 0.863209. And we use the same technique to find the error. We subtract the real value, the error from the real value. So my real value is 0.863209. Subtracting our approximation of 0.896841. You can see why calculators are pretty much necessary for this type of lesson. And then we would get a difference of 0.033632. And just as we anticipated, this estimate is not as accurate as the one that we did at 1.2 for the reasons that we talked about. You know, it's farther away from the center of the polynomial, which is 0. So that was the comparison between the two. Okay, questions? Okay, let's go to our next slide. A couple of more examples. All right, on this one, we're looking for a Taylor polynomial of degree n equals 6, a 6th degree Taylor polynomial that is centered at 1, c equals 1. All right, so same technique as we used for the Maclaurin. We're going to have to find, actually in this case, the first 6 derivatives, and then we're going to have to evaluate them at 1. Okay, not at 0 this time, but at 1. All right, so I have my scratch paper over here. The first derivative of natural log of x is 1 over x. Now, I'm not going to write it in fraction form just because I don't want to mess with the quotient rule. I'm going to write it as a negative exponent. I'm going to write it as x to the negative 1. So f prime of x is x to the negative 1. So f prime of 1, I substitute a 1 in there and I get 1. Okay, so let's do our second derivative. So we've been going back and forth between integration and derivatives so much. I'm hoping that we're good with this. We're doing derivatives now, so remember we bring that down, so it's a negative x. We subtract 1 to the negative 2. So I substitute a 1 in there, and I get, what, a negative 1. So my third derivative is 2x to the negative 3. I substitute a 1 in there, and I get 2. Our fourth derivative is negative 6x to the negative 4, and I sub in a 1, I get negative 6. My fifth derivative is 24x to the negative 5th, and my fifth derivative value at 1 is 24. And then my sixth derivative is, what did it turn out to be, negative 120, negative 120 x to the negative 6, and my sixth derivative value at 1 is negative 120. All right, let's create our Taylor polynomial. All right, so this is going to be P6 of x, and I'm always putting the function value in first. So I take a 1 and plug it into my original function. Natural log of 1 is 0, and you don't have to write it. I'm just going to work through the formula so you can see where everything's coming from. Then we go to our first derivative. Our first derivative value is a 1, and then we multiply it times, it's to x minus c, and our c value is 1, so it's going to be x minus 1 plus our second derivative value is a negative 1, so negative 1 over 2 factorial times x minus 1 squared. See how handy it is that those numbers are the same? It just kind of helps the second derivative value over 2 factorial, and our power is a 2. Just kind of helps us stay focused. Our third derivative value is 2. So 2 over 3 factorial, x minus 1 cubed. Fourth derivative, negative 6. So negative 6 over 4 factorial, x minus 1 to the fourth. Let's see, fifth is 24 over 5 factorial, x minus 1 to the fifth. And finally, our sixth derivative, negative 120 over 6 factorial, x minus 1 to the sixth. There's going to be a lot of prettying up there, isn't there? So we have a calculator. I would, put all those fractions, those factorial fractions in my calculator and do, math, enter, turn it into a simplified fraction. And when I do that, alright, so the prettied up form, this goes away. I'm left with x minus 1, and I usually do just leave them in parentheses just because. I mean, just so to show all the different terms, just to make it clear. The first one turns into minus 1/2 times x minus 1 squared. The next one, 2 over 3 factorial. 3 is, 3 times 2 times 1. That actually turns into 1/3 x minus 1 cubed. The next one simplifies to 1/4 x minus 1 to the fourth. The next one, are we seeing a pattern here? Isn't that a totally cool pattern? I mean, how 24 over 5 factorial is actually 1/5. I just think that is so cool. So 1/5 to the x minus 1 to the fifth. And what do you think about this 120 over 6 factorial? It's actually 1/6. Yeah, it simplifies to 1/6 x minus 1 to the sixth. So there's our polynomial. To find P6 of 1.8, yes, we would have to substitute 1.8 into everywhere there's an x and let our calculator do all of the work for us. Unless you want to do it by hand, that seems like a painful thing to do, but maybe somebody in here wants to do that. I don't know. P6 of 1.8 turns out to be 0.570112. See, I already did it for you, so you don't have to do this one. Alright, then the actual value, we would get our calculator and we would put 1.8 into natural log. So f of 1.8 is natural log of 1.8, which is 0.587786. 0.587786. Our error is real minus the approximate. So 0.587786 minus 0.570112. And the error is 0.017674. Now, this I find a little strange because we're out to the 6th degree, and our approximation really is not as good as the sine one, right? Which means that the natural log looks like a little bit more difficult to approximate than the sine. I guess because sine is, it curves kind of like a polynomial, and natural log just doesn't really do that. So its approximation, even though we're out kind of far, is not as good. Alright. And that is a typo. That should be a 6. Alright. Our last problem, suppose that g is a function which has continuous derivatives and then it gives us a bunch of function values and derivative values. Notice where our values are. So what had our polynomial better be centered at? 2, or we're in big trouble, right? We wouldn't have anything to work with. We need to be, and luckily it is centered at 2. So they want us to write the Taylor polynomial of degree 3 for this function centered at 2. So P3 of x is going to be, remember we always start out with our constant. In this case, that's 3. G of 2 is 3. Then our first derivative times x minus 2, because we're centered at 2. Our second derivative, 7 over 2 factorial, x minus 2 squared. And our third derivative, negative 5 over 3 factorial, x minus 2 cubed. And then we just pretty it up a little bit. And we get 3 minus 4. And I just leave it factored like that. There's no sense in distributing combining like terms. Just leave it like that. Plus 7 times x minus 2 squared over 2 minus 5 times x minus 2 cubed over 6. And that's our polynomial. Okay, we doing okay? All right.